And his bachelor degree from Lanzhou University in 2014, and his PhD from the East China Normal University in 2019. In 2020, he joined the Westlake University as a postdoc researcher in the School of Engineering. This year, he took a position as a research assistant professor in the same place, the School of Engineering at Westlake University. His principal research interest lies in the fields of chemical oceanography and marine biogeochemistry, specifically focused on the submarine groundwater discharge and related environmental impacts in typical estuaries and coastal ecosystems, such as mangroves, salt marshes, seagrasses, sandy beaches, and coastal systems. Until July this year, he has carried out about 500 days of field work. That's amazing. And today he's gonna give us a talk about, the title is the Porewater exchange and the related carbon sink potential in mangroves and salt marshes. So, Xiaogang, I think time is yours.
Okay, Rachel, thank you. Yeah, share my screen. So hello everyone, can you see my screen?
Yes, and your sound is also loud and clear.
Okay, that's great. Okay, so thanks so much, Rachel, for organizing this talk today, and also thank you everyone for participating my talk today. So my name is Xiaogang Chen, and from the Westlake University. So it's a great honor for me to share my research work here today. As Boto said, my principal research focuses on the summer groundwater discharge or Porewater exchange and related the environmental effects in the coastal ecosystems, especially for the coastal wetlands, such as mangroves and salt marshes. So today my topic is about the Porewater exchange and the related carbon sink potential in mangroves and salt marshes. So for this talk, I will give an introduction from these 4 parts of 4 questions. So first, what is the coastal carbon sink potential? Second, Porewater drive exports the missing carbon sink in coastal carbon systems. And the third one, that Porewater exchange represent a mechanism for long-term carbon storage. And last one, I will introduce search for emissions offset carbon sequestration in coastal wetlands. So first, I will give an introduction for the background, blue carbon sink potential. So as we know, the plants can fix large amounts of the atmospheric CO2 and while the photosynthesis and the release of the CO2 through the respiration. So the net primary productivity is the difference between the photosynthesis and the respiration. So now we can think about a question, can net primary productivity be translated into the carbon sequestration? The answer is yes. Sorry. Okay. So there are kind of aquatic systems such as the mangroves, salt marshes, and seagrasses. And these wetland vegetations can fix atmospheric CO2 and store this carbon into a sediment. And part of the sediment carbon can be exported via the Porewater exchange and the carbon outwelling process. And also some of the greenhouse gases, such as CO2 and CH4 from the Porewater exchange will be released back into the atmosphere. So we call these aquatic systems coastal blue carbon systems. And the coastal blue carbon is recognized as the carbon sequestration and the stocks in the coastal areas. And these blue carbon systems occupy less than 0.2% of the global coastal area, but they contribute more than 50% to the ocean organic carbon storage. And in this style, when we compared the coastal blue carbon systems with the terrestrial forest, we can see here the global area of this coastal blue carbon system is 1 to 2 orders smaller, magnitude smaller than this that of the terrestrial forest, but the vegetated coastal habitat per unit area to long-term carbon storage in these coastal blue carbon systems was significantly higher than the terrestrial forest. So we can see the global carbon barrier from these blue carbon systems were equivalent to that from the terrestrial forest. Actually, there were a lot of studies about the carbon barrier in the coastal wetlands, but the Porewater exchange of the groundwater flow has not yet been considered in the saltmarsh carbon budget, but may has the perceived contribution of these coastal wetlands to the global carbon budget. This is a very important studies about the mangrove carbon budget, and the authors tried to estimate all the mangrove carbon sources and sinks, but they found large amounts of the carbon was missing. So this suggests that this carbon may be exported to the coastal waters via Porewater exchange of the groundwater flow. So now we know the Porewater exchange is very important. So so we need to quantify the Porewater exchange and the related carbon fluxes. So my second question, Porewater drive export the missing carbon sink in coastal carbon systems. So in this slide, first I'd like to introduce the nature groundwater tracers, such as the radon and radium. So as we know, the radium is a very powerful tracers because we know the radium has 4 radioisotopes: radium-223, radium-224, and radium-228 to radium-226, and they have different half-lives from 7 days to 1,600 years. So that means they can trace different time scale process, ocean process. But for each radium samples, we need a lot of waters. For the surface water, we need about 20 liters, and for the open ocean, we need at least 50 liters. So sometimes it's really hard to get so much water, especially in the coastal wetlands. So actually, for me, I really like the trace radon because for the radon, for the Porewater sample, we only need 250 milliliter water, and also we can measure the radon continuously. But radon also has its disadvantage because the radon's half-life only 3.8 days. So that means radon can't trace the large-scale process, large-scale ocean process. So this is experimental setup for the coastal wetland. For the surface water, we installed some sensors such as the XO3, AZM, USB, and also hydrolab current meters to measure the temperature, salinity, dissolved oxygen, pH, also the water depth and the current speed. And to analyze the greenhouse gases such as the CO2 and CH4, and also the radon, the surface water was pumped into a gas calibration devices, and then the gases were pumped into the dry rat, and after into the dry rat to dry the gases, and then pump into the picara and the red salmon, and finish the analyzing of the greenhouse gases and the radon. So here we also installed a weather station, atmosphere 41, to measure the wind speed and the rainfall, because the wind speed is very important for the radon mass balance model. And also we collected some other samples such as the radio, carbon, nutrients carbon, and also some alkalinity samples, and bring back these samples to the laboratory. So from this slide, we also can see here, if we do some works for greenhouse gases, it seems the radon is good. Here we can measure these samples, use this closed loop here. So we use the radon mass balance model to quantify the Porewater exchange rate and related the Porewater exchange rate. So for this radon mass balance model, that means the radon sources equals the radon sinks. So we estimated all the radon sources and the radon sinks, such as the mixing loss while the tidal pumping, and also the radio 226 decay, radon decay, the diffusion, the radon diffusion from the sediment, and the radon emission, atmospheric emissions. And also sometimes if there have the significant contributions from the upstream, so we also need to consider the upstream input for this model. Then we could get the Porewater exchange rate based on this model. And this model has has widely used in the coastal wetlands. So now I'd like to introduce some study cases to introduce the Porewater exchange and related carbon fluxes in the coastal wetlands. So for the mangroves, our study site is Westlake. It's a mangrove bay in China. And for this, here we conducted the time series observation at the mouth of the bay, and also collected the groundwater and Porewater samples, also the river water and the sediment. So we use the radon mass balance model to quantify the groundwater flow and the related carbon fluxes, including the dissolved organic carbon and the dissolved organic carbon. Then we rebuilt the DIC-DOC budget, DIC-DOC budgets. And in this budget, in this new budget, including the SGD and contributions. So from this budget, we can see the groundwater flow groundwater derived carbon fluxes exceed the local river contributions, and these SGD derived carbon concentrations contribution more than 70% of the total dissolved organic carbon and the dissolved inorganic carbon input into this mangrove bay. So then we upscaling to this, combined our result with the literature data. We upscaled to the global mangrove area, and we estimated the global carbon fluxes while the groundwater flow in mangroves. So based on the result, the global carbon fluxes while the groundwater flow into the mangroves may be equivalent to 29 to 48% of the global river contribution. And also based on the local and global result, we can see the SGD is a major component of the coastal carbon budget, and that accounting for SGD helps to reduce uncertainty in the mangrove blue carbon budget. So for the salt marshes, our study site is a Dafeng Elk National Nature Reserve in Yancheng, Chinese mangrove, a Chinese salt marsh creek here. So in this study site, we also conducted time series. We considered the tidal pumping and the seasonal variation, and we conducted the time series of the variation here at the creek mouth. And also we collected the Porewater samples at the downstream site, mid creek site, and also upstream site. And for each site, we collected the Porewater samples at the high tide, at the low tide mark, mid tide mark, above tide mark, and high tide mark, and above high tide mark. So that means we installed 12 Porewater bores in this study site. So this is a major salt marsh vegetation in this reserve, and this is the elk in the reserve. Just have a look. So this is a time series observations for the surface water. So for the left figure, we can see here the radon. So radon displayed a tidal trend with the lowest values at high tide and highest values at low tide. And also for other parameters such as temperature, salinity, oxygen. Also, we can see the CO2, CH4, dissolving organic carbon. So all these parameters change significantly with the tidal pumping. So from this side, we also can see the radon is good tracers for the salt marsh carbon, And here we analyze the correlation of the greenhouse gases and carbon with the radon concentrations. So we can see the for the surface water, we can see the DIC, DOC, CO2, CH4 concentrations had good positive correlations with the radon concentration. And also for the Porewater, we can see Porewater, the DIC, DOC, CO2, CH4, these carbon Porewater concentrations, and also the radon concentrations were significantly higher than those from the surface water. So this provides a strong evidence that Porewater exchange is a source of the salt marsh surface water carbon. So based on our observation result, we built 2 groundwater surface water exchange mechanisms. So here including the crab barrel flushing and the spring nip exchange. So for here, for the semi-diurnally time scale, so the flushing of the crab barrel leads to the higher carbon concentrations at low tides and the lower carbon concentrations at high tides. And also for the spring nip exchange, spring nip time scales, the older groundwater enriching carbon concentrations seeps into the tidal creek as the amplitude decreases. So this leads to the higher carbon concentrations during the nip tides and the lower carbon concentrations during the spring tide. So in our study site, both these 2 exchange mechanisms occurred in the wet season, but only the spring nip exchange occurred in the dry season due to the crab hibernation in the dry season. So also we use the radon mass balance model quantified the Porewater exchange rate and the related the DIC, DOC, and CO2 CH4 fluxes. And we also estimated the carbon outweighing fluxes and the greenhouse gases emissions. Then we built the carbon budget in these salt marshes. So from this budget, we can see the Porewater derived carbon fluxes were about 1.2 times higher than the carbon barrel in this salt marsh. So that means the exported carbon represent a major carbon sink in the study site. And also this discovery can potentially lead to an important revision of the salt marsh carbon budget. So in addition to the tidal pumping and the seasonal variation, here's we know the rainfall events have the potential to strongly alter the forces driving groundwater flow in salt marshes. But information about how the groundwater flow in salt marshes is driven by the primary is quite limited. So in our study site, in our study we can see the precipitation during the primary season. So here the primary season that means seasonal rainfall events. So in this during the primary season, the precipitation is relatively concentrated at that accounting for 40 to 50% of the total precipitation in the flood season in this study site. So also we conducted the field observations to confirm the effect of the primary on the Porewater exchange rate and the related greenhouse gases fluxes in this study site. So we for the surface water time series observation, we can see this slide here. For the surface water observations spanned from a spring nip tidal cycle to a nip spring tidal cycles with a total of 30 tidal cycles. And here the gray shandy represent the rainfall, represent the primary season. And during the primary season, 5 heavy rainfall events were captured during this period. So from this picture, we can see both the hydrological, such as the salinity, temperature, pH, oxygen current, and also the chemical parameters such as radium, CO2, CH4 will greatly influenced by the rainfall events. And especially here for the pH, we can see after the rainfall events, the pH was significantly decreased during the primary season. So we also use the rate mass balance quantified the Porewater exchange rate and related the CO2 CH4 fluxes. So this is the greenhouse gas fluxes, Porewater drive greenhouse gases fluxes per unit area, and this is total fluxes. So here we can see here the black dots represent the flux values during the pre-race season, and the red dots represent the flux value during the primary season. So we can see the Porewater exchange rate and the related greenhouse gases fluxes under the same tidal amplitude during the primary season were significantly higher than those during the no-race season. So that means that the Porewater driven greenhouse gases were not only controlled by the tidal pumping, but also controlled by the rainfall events. So here we also analyze the greenhouse gas fluxes, the relationship between the greenhouse gas fluxes and the salinity difference. Here the salinity difference, that means the salinity at high tide minus the salinity at low tide for each tidal cycle. So we can see this greenhouse gas fluxes had good positive correlations with the salinity difference. So that means the salinity difference in each individual tidal cycle appeared to describe where the combined effect of the tidal pumping and the rainfall event on the Porewater driven greenhouse gases fluxes. So this previous studies found that coastal wetland export large amounts of the alkalinity and the dissolved inorganic carbon to the coastal waters, and then the CO2 were released back into the atmosphere very quickly. So this leads higher pH and alkalinity than the open ocean in this buffer zone. So due to the lower alkalinity input from the riverine and the basin sources, coastal wetlands derived alkalinity export might be one of the largest sources of the alkalinity to the coastal ocean and provide a localized buffering effect against coastal acidification. So in our study, we can see the Porewater derived greenhouse gas fluxes and also the surface water greenhouse gases inventories during the primary season significantly higher than those from the no-rain season. So large Porewater derived CO2 during the primary reduced the pH of the saltmarsh surface water by about 0.2, highlighting that the primary can have CO2 fluxes and inventories through the Porewater exchange in saltmarshes and offset the potential of the buffering coastal acidification in our study site. So yes, now we can see the Porewater derived large amounts of the carbon fluxes in coastal wetlands. So my third question, does Porewater exchange represent a mechanism for long-term carbon storage? So we know the pH of the seawater is about 8.1. So we can see the bicarbonate is very stable at these pH conditions. And we also know at both local and global scale, the DIC is the largest contributor of the lateral export in mangroves and salt marshes. So that means salt marsh and mangroves DIC outweighing can be a mechanism for long-term carbon sink potential to carbon barrier into the sediment, because alkalinity can be stored in the ocean for about 100,000 years. So were different. We can, for example, for the respiration, the delta alkalinity, delta DIC ratio is about minus 0.2, and for the denitrification, the value is about 0.9, and iron reduction 8.1, and sulfate reduction 1.0. And also for the, we can see the calcium carbonate dissolution is about 2. So based on this, we also did some works in our saltmarsh study site. We collected the sediment cores, Porewater samples, and also the surface water samples. So we can see this figure. We can see the alkalinity had positive correlations with the DIC concentrations, and also we found that the alkalinity DIC ratios were about 0.9 and 1.0. So from this, we can see this alkalinity and DIC generation is dominated by the denitrification and the sulfate reduction in our study site. It's not from the calcium carbonate dissolution, because some of my colleagues always ask me, they thought the alkalinity and the carbon should be from the calcium carbonate dissolution. Thus, from this study result, we can see it's not from the calcium carbonate dissolution in the coastal wetland. And also we know for the coastal wetland, the Porewater also release the dissolved organic carbon to the coastal wetlands. So we also did some works for the organic carbon in this saltmarsh study site, Chongming Dongtai. So this study site located at the Yangtze River estuaries. So in these studies, we found that these very complex molecules is the main component of the refractory dissolved organic carbon. And this refractory dissolved organic carbon contribute more than 60% of the dissolved organic carbon. Because the refractory dissolved organic carbon cannot be utilized by the microbes. So that means the refractory dissolved organic carbon also can be stored in the ocean for a long time. So RDO3 may represent another important mechanism for the long-term carbon storage in the coastal wetlands. But we only did this work in the Chongming Dongtan, these places. So for future work, we may check this result. We may do some work, similar works in other study sites. So yes, we know the coastal wetland release large amounts of greenhouse gases, also release large amount of greenhouse gases to the atmosphere. So and the greenhouse gases, especially for the CH4, it have the stronger global warming potential. So my first question: can CH4 emissions offset carbon sequestration in coastal wetlands? We know the CH4 has 45 to 96 fold greater global warming potential than CO2. So we checked them. We summarize several study cases and estimated the CH4 emissions. So for this study site, the authors estimated the CH4 emissions, and they found the CH4 emission could offset 5% of the soil carbon barrier in this study site, in these mangroves. And also in our study site, we estimated the CH4 emissions that could offset about 1% of the soil carbon barrier. And also here, this is a multi-species saltmarsh in China, Hangzhou Bay, these places. And we did similar works here, and we found the CH4 emissions could offset about 2% of the soil carbon barrier here. So from this start case, we can see the CH4 emissions in the coastal wetland could offset less than 5% of the soil carbon barrier. So that based on all this result, you can see the coastal wetland, mangroves and salt marsh are important, provide important carbon sink potential. Here I'd like to give some summaries and conclusions and short here. So first, in our salt marsh study site, we built 2 groundwater surface water exchange mechanisms, including the barrel flashing at the semi-diurnal time scale, and also the spring nip exchange at the weekly time scales. And also our studies results suggest the Porewater dried carbon fluxes were significantly higher than that of the carbon barrier in mangroves and salt marsh sediment. And Porewater derived carbon fluxes seem to be important in global mangroves and salt marshes blue carbon budget. Oh, actually, we also did some works for the global salt marsh blue carbon studies, but maybe because of the time, so I didn't show it here. But from our result, we also can find the for the salt marsh the Porewater derived carbon fluxes were significant in both the local and the global scale. And here, based on the alkalinity and the refractory dissolved organic carbon result, we can see the Porewater-derived carbon fluxes can be a mechanism for long-term carbon storage, similar to the carbon barrier in the sediment. And the Porewater-derived carbon fluxes were controlled by the both the tide pumping and the rainfall events. Actually, not only these two driving forces, also the seasonal variations, and also maybe the sea level rise and the maybe the global warming. All these parameters, all these driving forces can control the control the
Feel free to talk or raise your hand in the chat room. Okay, Isaac.
Hi, Xiaogang. Hi, Bochao. Yeah, good to see you.
Hello, Isaac.
Thanks for the talk. You're talking about those two mechanisms of recirculation, the spring nip and the crab barrels. So I think my thoughts is how can you kind of try to quantify those two things? And how can you separate the carbon from one mechanism that would be like a young carbon versus the old carbon that's like the bigger recirculation cell mechanisms? Are you thinking about that, Xiaogang? Any thoughts about that?
Yes, actually, we did some other works because in our study site for the saltmarsh this site, we find some springs for the along the creek. Find the springs, and Lin and another professor they said maybe this springs it's not from because the salinity is this spring water, the salinity is very high, always high, no fresh or fresh water. So this maybe this this spring water from the older groundwater, recirculated seawater, and it's also enriching higher carbon concentrations in this groundwater. But we just want to use some other isotopes. It's not radioisotopes to separate it, but we just try. We want to try and find some. We want to separate this, but we just try. We didn't get this result. Sorry.
To follow Isaac's question, so you said there's a spring, but it's not fresh. Is it?
Yeah, it's not fresh. Yeah, there's some because they use some physical method and find this groundwater from the very deep, very this water is not several meters. It's very deep groundwater from the deep groundwater. So, but they use the physical method, not tracers.
All right. So I said, and I see another question from the chat room. One quick question: have you ever measured the hydraulic conductivity of the saltmarsh soils? Can the hydraulic gradient and the hydraulic conductivity support your large pore water exchange rate? I have tried in Hong Kong. Okay, I think Liu Yi just has these two questions. about
Yes,
the
and,
hydraulic conductivities.
yes, actually, I didn't do some works for the conductivities. So sometimes we use the tracer. Actually, we use the tracers. It's a little bit higher than the physical method. But I'm not sure because we use the tracer estimated all the groundwater fluxes that leaving from the salt marshes or the mangroves. But I didn't do some works for East side. Yeah.
Yeah, I think that's somehow go back to Isaac's question again. What is the main mechanism for the Porewater exchange? Is it the fresh component or terrestrial component or recirculating component?
Sorry, Bashar.
Anyway.
Okay.
Anyway, so I saw Alisa is raising her hand. Alisa, please.
Yeah, thank you. My question, you had one slide, you had that one estuary where where there was the plum rain and the salinity changed so much once the rain started. And there was a lot on that slide, so I think it's probably on there, but I wasn't able to pick it out. I just wanted to ask you.
Yeah.
I have an estuary that's mostly saline, but when we get a big rain event, it becomes fresh. And what I've seen there is that the DOC concentration just skyrockets when there's a lot of fresh groundwater discharging. So you get the rainfall and, you know, the immediate input into the estuary may not add DOC, but after that immediate rainfall event, then you see still a lot of freshening over multiple tidal cycles. And the DOC just goes way up because the DOC concentration in the fresh groundwater is way higher than in the salty groundwater. Or fresh streams are running into what we think of as a very lagoonal estuary. I mean, there isn't big rivers coming into it, so we think that there's no fresh water, but I'm saying this very badly. My question is, where did the fresh water come from after the big rain event? There's still clearly a lot of fresh water in your estuary. Is it fresh groundwater discharging directly to the estuary, or is it surface creeks and things that we don't see in the satellite photos? Oh, yeah, that one.
Yeah. Yeah, this one. Here, yes, we can see here. So we can see here the salinity after this rainfall events is decreased very significantly. So actually here we know because it's very strong rainfall events. So this should be from the dilution by the rainfall here. So then they will recover back to the normal. But sometimes you can, because this is primarily always some rainfall events in this side. So it's the salinity during the primary for events a little bit lower than before the primary season. Because in our study site here is no the upstream fresh water support. So I think so no fresh groundwater, no significant fresh groundwater contribution. Sometimes the salinity decreases almost because of the rainfall events from the rainwater.
Oh, so you're arguing that for this period where there's no rain, you have your significant rainfall event and the big drop in salinity, and you're saying that in that period afterward where there isn't any rain, but we're still seeing large changes in salinity, that That's not fresh groundwater, that's fresh surface water that's traveling through your
Yeah.
site? Okay. Oh, I see, and you weren't monitoring DOC. Ah, too bad. Thank you, I appreciate it. It was a good talk.
Thank you, Wes.
All right, thanks, Lisa. There's another question from Chen Wang. As we know, radon is a good tracer. Did you use another tracer to estimate pore water? Maybe multiple isotopes will offer more confidence about your results.
Yes, actually, we collected we collected radium samples, but we want to use the radium sample to separate the different groundwater flow. Actually the pore water samples and also just I say the spring water samples, the radium is almost the same, so we can't separate that.
What do you mean the same? What do you mean?
Sorry.
What do you mean by same?
I mean the radium concentrations in the groundwater samples and also in the spring water samples, the concentration and the ratios were almost the same.
Okay. All right, there's another question from Denis. The question is, how do you measure aquatic fate, bacterial degradation, and particle scavenging in your DOC mass balance?
Sorry, actually, we didn't measure these samples. We use the literature data for this process in the carbon budget.
All right, any more questions?
Hey, Xiaogang, nice talk. I'm wondering.
Hello, Chen. Hey, Chen.
Hey, I'm wondering if you could talk a little bit more about this distinction between pore water exchange and outwelling of carbon, especially within the context of your kind of regional budget. To me, the pore water exchange and the outwelling are more or less the same unless you're accounting for the CO2 that's degassing during transit through the surface water system. So I'm just wondering if you could explain that in a little more detail.
So for the you miss the groundwater flow. How to you miss how to calculate this fluxes?
Just conceptually, what is the difference between the outwelling of carbon through the estuary and then the pore water?
Oh, okay, I understand. So here, further calculations for the pore water exchange, that means the water flux is released from the sediment. So, but what you see here, yes, here. So yes, the pore water exchange, the flux is that means the water flux is released from the sediment, and the outwelling fluxes, that means the carbon or the water that leaving the leaving all these salt marshes or mangroves. So because first the water and the carbon were released from the sediment. Then they were into the critical surface water and then transport to outside. So the carbon outwelling, that means from that flux is leaving from the salt marshes.
So I guess the question is, are they balanced then if what you're observing from exchange through the sediments is being transported to the coastal ocean there, or is there loss of CO2 or some other mechanisms that might make these terms not apples to apples?
Sorry, Jie. Sorry, Jie, can you repeat that?
I'm just wondering if the Porewater exchange flux here of carbon is then equal to the DIC outwelling or DOC outwelling that you're showing.
Okay, understand. Yes, you're right. So, because actually from the carbon transport from the creek water and to the coastal ocean, actually there are still other processes occurred, such as the organic carbon degradation, and also some greenhouse gases were released into the atmosphere before they exported to the coastal water. So the Porewater exchange sometimes is not equal to the carbon outwelling.
But it's not higher, right?
I see some other studies that it's different from different study site actually. Sometimes it's a little bit it's very different. Sometimes it's a little bit.
Thank you. Really great talk.
Thanks, Joe.
Thanks, Jia. Another two questions. One is if you observed a huge difference in your parameters, especially CO2, radon, and DO during the plum rain season and dry season. The second is if yes, then what were the major differences that you observed?
If you observe. Yes, actually, here. Yes, here. Yes, this is the observation data. So actually, but I didn't show it here. We checked the data, the CO2 CH4 data during the pre-race season and during the plumage season. So this is significant different. And also the fluxes, like here. Also, the fluxes were different as we calculated here. I didn't show the, actually we did some statistical analysis, but I didn't show it here. Actually these two periods, the concentrations were significant different.
Okay, there's a question from Bill Burnett. His question is, I have a question about the plots of radon versus different carbon forms.
Yeah,
Hi,
thanks,
Bill.
Chair. Very impressive data set and very nicely presented too. Could you show that slide? You had some XY scatter plots of radon versus different forms of carbon, CO2, methane, etc. Yeah, that looks like it. Yeah, that's it.
Yeah.
In the the methane versus radon. The you have the different
Here.
colors represent different sampling periods.
Oh, sorry. Yes, it's different type and different seasonal.
Yeah. So under different conditions, the regression lines that you drew, is that through all of the data, or are you selecting one fraction?
All this data.
It's all the data.
Yeah, all this data. Yeah.
Yeah. Okay.
Because
Looking at
for the Porewater samples, actually for each season we only collected one time. So that means for the spirit tide and nip tide we only collect one time for the Porewater samples.
Okay. Yeah. In the methane versus radon, let's see that orange symbol. These, let's see, that represents neap tide in December. That seems to be particularly well correlated, doesn't it? It seems like, that would be of course, it is a log scale, so it might be, misleading in some way, but it looks like that's a very strong correlation. I wonder, why is that better correlated than most of the others? If in fact it really is, maybe it isn't.
You miss some missing?
I'm just wondering why this neap tide December, these orange circles seem to have I bet if you drew a line and a regression line, it would be a very strong correlation, stronger than most of the others, if not all the others. I just wondered why, that's all. It's, yeah.
The nip tide here is in the December here.
Mm-hmm.
Oh, it means this like a circle here, but actually here, you see, here also have some samples during the nip tidal cycle in this season.
Uh-huh. Yeah, looking at the other plots, like the DOC and the DIC, CO2, the neap tide doesn't show that strong Chen that it does for methane. And I just thought that was curious.
Yes. So looks like a circle. For nip tide cycles.
Mm-hmm. Yeah. Okay. Yeah. Thanks.
Thank you.
Nice presentation.
All right. Any other questions? Okay, if you guys don't have any questions, we're gonna thank Xiaogang again for the wonderful talk. Nice work, Xiaogang.
Yeah.
Thank you so much, Pochao. And thank you, everyone.
All right. Goodbye, everybody.
Okay.
Bye-bye.
See you next time.
Thank you. Thanks, Bill. Thanks, Isaac. Wilson.
Bye-bye.
See you, Bill.